Hello and welcome to the first video about the security of quantum key distribution. This is a series of talks that was originally intended to be held as a seminar where students are introduced to the concepts of quantum cryptography, more precisely quantum key distribution protocols and the security of such protocols. But unfortunately, because of the current situation, it is not possible to hold any lectures or seminars at the university, so I decided to make some videos instead. The goal of the seminar is to understand how and why quantum key distribution protocols are provably secure. This means what kind of physical or quantum mechanical phenomena make it possible that we can rely on the security of such a protocol, no matter how much power a possible adversary might have. To achieve this goal, we first have to understand how quantum key distribution protocols work. So we will go through every stage of the protocol in detail and understand what is happening. After we have understood this part, we are able to define what we actually mean when we say security. And when we have found a suitable definition, we can then study how we can prove that a given protocol is secure. Along our way, we will, of course, encounter several mathematical concepts and theorems, for example, quantum channels and measurements, the no-cloning theorem, and entropies. This first video serves as an introduction, or as I rather like to put it, as an invitation to the seminar. So we will start with some classical cryptography, where I will show you what the problematics behind classical encryption schemes are, and also what we will actually need to securely encrypt and decrypt messages. This will then motivate the use of quantum mechanics, and we will have a look at how quantum key distribution actually works by studying a specific example, namely the so-called BB84 protocol. This is in fact the protocol that got the whole thing started because it was the first quantum key distribution protocol that was proposed in 1984. Through the study of this example, you will get a rough idea of the different stages of a quantum key distribution protocol, and actually this serves as a nice summary of what awaits you in the upcoming videos. Okay, so let's get started with some classical cryptography. Cryptography is an old topic. It has played an important role throughout history, at least since the ancient Greeks, and especially in times of war. You may have seen the movie The Imitation Game, which is about how the British, especially Alan Turing, have tried to decrypt the messages that the Germans sent in the Second World War using the Enigma crypto system. And this is just one example of how cryptography influenced the outcome of a war. So I want to show you a different cryptography scheme, which is called the Caesar cipher. So first, some notes about the terminology that we use. We always distinguish between the plain alphabet, which is used to write the original messages in, and the cipher alphabet, which is the alphabet we write the encrypted messages in. Okay, so the Caesar cipher is a quite simple encryption scheme. It basically tells you to move each letter of the alphabet 3 steps further in the alphabet. This means that the letter A is encrypted as a D, the letter B is encrypted as an E, and so on, until we get to the letter X, which is then we start again at the beginning of the alphabet and encrypt X with an A, Y with a B, and Z with a C. Of course, you can do it with moving the alphabet more or less steps further, but moving it 3 steps further was how it was originally used by the Romans when they wanted to send messages of military significance. Okay, suppose I want to send a message using this encryption scheme. Say I want to tell someone that we're meeting at the apple tree. Then I have to look up how the letter M is encrypted, which is with a P. Next, how the letter E is encrypted, which is an H, and so on. Looking up all the letters yields this message, this ciphertext, which is some unreadable sequence of letters. Okay, suppose I have encrypted this message. I'm sending it to the person which is intended to receive it. And this person now, of course, needs to know how to decrypt the message. But what about people who are not intended to read the message, like people who want to intercept my communication? For them, this text looks like some unreadable thing, but actually, even though at first glance it doesn't seem easily decryptable, there are ways to decrypt these kind of messages. The problem is that in every language, not all the letters of the alphabet are equally distributed. So, for example, in the English language, the letter E is most frequently used. You can also see it in our text. We have used the letter E 6 times, as you can see here, which is, like, if I see it correctly, the letter that's most used in this message. And also, the letter T is the second frequent letter in the English alphabet, and we have used it here 4 times. So this seems like a very typical sentence in the English language. And by doing such a frequency analysis, it is not that hard to actually decrypt messages. Of course, it gets easier with longer text, because with shorter text is more possible that we have a text with an atypical distribution of letters. Okay, but if you have like a normal sentence in the English language, by doing frequency analysis, you're quite likely to recover the original message. Okay, so if we actually want to be secure that our message cannot be decrypted, this is not the kind of scheme that we want to use. You can now, of course, think of more sophisticated methods. Like, for example, shuffling the letters completely, which gives you actually lots of different ways to encrypt the alphabet. But all these encryption schemes, they have the problem that with frequency analysis, they are quite likely to be decryptable. Also, you can think about using devices that help you encrypt things. Like maybe they use a trick or something, or some code you need. But all these devices have the problem that if you know how they work, it's easy to decrypt them. Okay, but fortunately, there are encryption schemes which are provably secure. So one of them is the so-called one-time pad, which I will explain to you in the following. First, I will show you the setup. This is a very typical setup that we will encounter through this seminar very often. Every time we have some protocol that involves 2 parties who want to communicate to each other, we usually call them Alice and Bob. And here, the letter M represents the message that we want to send. SA and SB are the keys that Alice and Bob hold, which they use for encryption and decryption. And the letter C stands for the ciphertext, so the encrypted message that Alice is sending to Bob. Okay, when we now talk about messages and keys, what we actually mean is bit strings. So from now on, every time I say message or key or ciphertext, I mean a bit string. Okay, let's see how this protocol works. So the first step is encryption. Alice encrypts her message M using her key SA by doing binary addition. This means that if you add 2 different bits together, then you get a 1 bit, and if you add 2 same bits together, you get a 0 bit. We'll see an example of that in a second. The second step is then the transmission. So Alice sends the ciphertext C to Bob over a public channel. This means everybody can listen to it. So also an adversary who would like to intercept our communication and read our messages, he's able to read the ciphertext. And then the last step is the decryption step. So Bob receives the message and he decrypts it by using his key SB, again by doing binary addition. And you can see that the message that Bob receives in the end, M prime, is actually the same as M. So if you look at an individual key bit, Mi prime, then this is the same as the binary addition of the ciphertext, more precisely the respective bit of the ciphertext Ci, binary added to the ith bit of the key that Bob holds SB, and this ciphertext Ci was originally created by doing binary addition of the message bit Mi with Alice's key bit Sai. Okay, when we now assume that Alice and Bob have perfect keys, so their keys are exactly the same, then we know that SA and SB are the same bit strings. So the message, the key bit SAI is the same as the key bit SBI, and if we add two equal bits together, we always get 0. So Mi binary added to 0 is always just Mi. This shows that Mi prime is the same bit as Mi. So Bob has received exactly the message that Alice wanted to send. Of course, this is an idealized scheme, because in reality we have to consider losses, or that maybe the bits are not exactly equal. But for now, we don't care about these things. In our ideal world, Bob receives exactly the message that Alice has sent without any errors. Okay, let's see one explicit example of this. Say Alice wants to send the message that is depicted here in terms of bits, which is 0110100. She does this by using her key, which is 1011101, and binary adding these two results in the ciphertext 1101001. So as you see, every time we have added two different bits, like the first bit 0 plus 1, the ciphertext is 1, and every time we added two same bits, as the third bit 1 plus 1, that equals 0. Okay, now Bob receives the ciphertext. His key is the same as Alice's key, and he's now doing again binary addition of C and SB to receive the message he was intended to get. And as you can see, this results in exactly the same message that Alice has sent. Okay. So, as I told you, this encryption scheme is actually provably secure. And actually, the term for this is information theoretically secure. This means that the adversary can get no information about the message that was sent through the ciphertext. As you've seen in the protocol, the ciphertext was sent through a public channel, but when the scheme is information theoretically secure, then reading the ciphertext doesn't give an adversary any information on the message. Okay, so this protocol is information theoretically secure, that was proven, but the drawback is the key has to fulfill several things. Let's look at that in more detail. So the key has to be truly random. So that means the bit strings that Alice and Bob have as their keys, they have to be truly random sequences of bits. The next thing is that the key has to be at least as long as the message. As you've seen, the encryption scheme was binary addition. So if we don't want to use parts of the key twice or so, then the key has to be at least as long as the message we want to send. The third part is that the key can never be used like in whole or not even partly. As you can see, imagine you have used the key S twice, which results in two different ciphertexts, C1 and C2. Then C1 was originally created by doing the binary addition of M and S, and C2 was created by doing binary addition of N and S. And if an adversary has now recorded all the ciphertext you have sent, then he can, in principle, do binary addition of the first and the second ciphertext. And as you can see, since the binary addition of S with itself equals 0, this binary addition of the two ciphertexts equals the binary addition of the two messages. Of course, this is not directly the message that was sent, but it contains some information about the messages. And if the adversary is very clever and he listens to lots of communication, so he gets lots of ciphertexts and he gets even more combinations of messages, then it is possible that he will be able to retrieve the original messages that were sent. And you definitely don't want to do that. You don't want that to be able to happen if you say your protocol is provably secure. And the last requirement is that the key has to be kept completely secret. So no information about the key can be given to the adversary. If these 4 requirements are fulfilled, then the one-time pad is a provably secure encryption scheme that you can use without having to worry about anyone intercepting your communication and revealing your secrets. This is nice, but the problem lies in all the requirements that we have for the key. So how do you create a key that is truly random? And of course, Alice and Bob have to share the same key. No information about the key can be given to the adversary. This is quite difficult because, like, what you don't want to assume is that the two parties, Alice and Bob, just meet with each other and agree on a key. You don't want that because then they could just share the messages they want to send. So what is needed is some sort of device that we will call here the ideal key generator that outputs keys to Alice and Bob, but also keeps into account that Eve in general is able to intercept communication and tries to get information about the key. Okay, so this ideal key generator, he has 3 involved parties, Alice, Eve, and Bob. And what we want is that it outputs keys SA for Alice and SB for Bob. But if it recognizes that Eve interacts too much during the key generation process, that Eve gets too much information about the key, then it just aborts. Okay, what are the requirements that we have for this kind of ideal key generator? So the first thing is that we want the keys to be correct. So as we said, Alice and Bob have to hold the same bit string as their keys. And technically this means that the probability that the keys differ, but the protocol does not abort, is small. So if for some reason the keys are very different, then the protocol should recognize this and it should just abort. Okay, so this probability should be smaller than epsilon, where epsilon, of course, is some arbitrarily small constant. The second requirement is that the key has to be close to a perfect key. This is very similar to the requirements that we had for the key in the one-time pad encryption scheme. So we want that Eve doesn't have any knowledge of the key, and that the individual key bits are uncorrelated. Okay, but how can we build such a device that outputs these kind of keys? That we then can use in the one-time paired encryption scheme. So this is the most difficult part. How do we create keys for Alice and Bob that fulfill all these requirements? And this is exactly where quantum mechanics comes in. So in the following, I will show you the specific quantum key distribution protocol BB84. We will go through the several steps, and you can see what kind of stages there are in such a protocol. But before I show you the protocol, we have to talk about how we can encrypt bits into quantum states, because that's what's needed in a quantum key distribution protocol. That's why we will shortly talk a bit about the polarization of photons. You can use the polarization of photons to encrypt bits into quantum states. And you can do it in the following way. So we consider linear polarization. That means that the oscillation of the photons only occurs in the plane, in one direction. And we distinguish two different bases, namely the rectilinear basis, which is horizontally and vertically polarized photons, and the diagonal basis, where you have photons that are polarized either in the plus 45 degree polarization or minus 45 degree. Okay. Given one basis, how do we distinguish between the different basis states? You can do this by using polarization filters, which you can think about as the following device. So if you have a vertically polarized photon, which passes through the filter, it will be deflected to the right, and a horizontally polarized photon will be deflected to the left. That's how you distinguish these two basis states. Okay, but what happens when a photon that is encoded in the diagonal basis passes through a polarization filter, which is intended to distinguish photons in the rectilinear basis? Then the following happens. The photon is the state of the photon is changed. So the polarization of the photon is changed either to a horizontally polarized state or a vertically polarized state. And this appears completely random. So with equal probability, we have a horizontally polarized or a vertically polarized state in the end. This also means that when such a photon passes through this filter, all the information about the original polarization will be lost. This will be very important during the protocol, because this means that if I measure a photon which is encoded in the diagonal basis, when I measure this in the rectilinear basis, then I do not get any information about the photon. Okay, with this in mind, we can now go on to the protocol. And first, we fix the encoding of our bits. So given the diagonal and the rectilinear basis, we choose for each of the bits 0 and 1 which polarized state corresponds to which bit. Okay, then the basic setup is the following. Again, we have our two parties, Alice and Bob, who want to communicate with each other. They want to create a secret key. So a key that can then be used in the one-time paired encryption scheme, for example. Alice and Bob have access to a quantum channel where they can send quantum states. For this example, we only need a quantum channel where Alice can send quantum states to Bob, but in principle, you could have a channel where also Bob can send quantum states to Alice. They also have access to a classical channel where they can both send classical messages back and forth. Then, of course, we have an adversary. There's Eve. She has access to the quantum channel where she can manipulate states that are sent via the quantum channel. She can also listen to the classical channel because the classical channel is a public channel. But she is not allowed, she cannot change the messages that are sent over the classical channel. Okay, then let's have a look how the protocol works. So the first part is that Alice chooses a random bit string. Here's an example bit string of 6 bits where she chose 010100. She then randomly chooses an encoding basis for each of the bits. So here she has chosen like a series of different encoding bases, and she then uses these bases to encrypt the bits from the bit string. As you can see, this results in photons in several states, and these photons are then sent to Bob. Bob chooses, again randomly, the decoding basis he wants to use and decodes the state Alice has sent. He gets also a bit string, but now, as you can see, if you consider the first bit, Alice has chosen the rectilinear basis to encode the bit, but Bob has chosen the diagonal basis to decode the bit. So even Alice was intended to send the bit 0, Bob has received the bit 1. Here I've just chosen one of the two possibilities. Of course, since Bob has chosen the wrong basis to measure the photon, 0 and 1 can occur with equal probability. Yes, but every time Alice and Bob have chosen the same basis, they also have the same bit as a result. Okay, so now Alice and Bob both have these bit strings, and this is basically the quantum phase. So everything quantumly is now finished. The quantum part is only encoding and sending photons. Okay, but Bob has now this bit string, which is not equal to Alice's bit string. So what do? Well, first, they check at which points they have chosen different bases. So Bob announces his choice of basis, and Alice then says, okay or not okay. And as you can see here, the first and the fourth bit, there Bob and Alice have chosen different bases. So these bits are discarded. They are not used in the following process anymore. But 4 bits are okay. Bob and Alice have chosen the same basis, so they can use these bits to further generate their key. The next thing they have to check, so the shared information they both hold is now the string 1000. The next thing Alice and Bob have to check is if there's happened some eavesdropping. So if Eve has intercepted the communication, Bob and Alice can detect this, as you will see in an example in a minute. So assume there's been no eavesdropping, Eve hasn't intersected with the quantum states at all. Then Bob will reveal some example bits. Alice will check them. And if they're okay, then Alice and Bob know that there hasn't been any eavesdropping. And they can be sure that they both share the same random bit string. Of course, they have to discard the bits they have been used for the checking because they have been revealed over the classical public channel. Hence, the key bits they end up with are only like a shorter amount than the one Alice has started with. So the resulting key bits are now 1 and 0, and Alice and Bob can now be sure that they can use this as a secret key in any application. Okay, but this was the case without any eavesdropping. What happens if Eve intercepts the communication? Okay, let's have a look at an example. So consider the situation that Alice wants to encode the bit 0 into the rectilinear basis, which yields a horizontally polarized photon that is sent over to Bob. Okay, so let's say in the first bit, Eve intercepts the communication, while in the second bit, she doesn't intercept it. Okay, so Eve intercepts the communication by just measuring the photon that was sent. And here she has to randomly choose one of the bases, because she doesn't know which bases Alice has used to encode the bit. So say she chooses the wrong basis. She chooses the diagonal basis. Then she gets a random result, let's say this one, which means that she now thinks this is equal to the bit 1. And this state is the state she has to send to Bob, because Bob awaits some sort of state. If there are too many losses in the communication, he will get suspicious. Okay, so she sends this bit to Bob. He chooses some decoding basis. Say he chooses the same basis as Alice. Then, in the case of the first bit, he will receive some random result, because he's measuring a diagonally encoded bit by using the rectilinear basis. But in the second case, he has chosen the right basis, so he will get the bit 0. Okay, say in the first case he got the bit 1, which is possible with a 50% chance. Then, if you remember, in the next step, where Bob reveals his choice of basis, in both cases, Alice will confirm that they have chosen the same basis, and they will be sure that they share the same information. So it is crucial that Bob also reveals some of the resulting bits, as you have seen before. So they can, because in this case, if he reveals that the first bit was 1, Alice will see that even though they've chosen the same basis, they didn't get the same bit. So they know that some sort of eavesdropping has happened. And Bob has to reveal enough bits so they can get a rough estimate of how much information was sent to Eve. And yeah, regarding on how much information was lost, they decide if they want to abort the protocol or if they still can get some key out of it. Because even though after this protocol, Alice and Bob don't share the exact same random bit string that is totally uncorrelated to Eve, they can still do something with the bits they have. There are two classical post-processing steps called error correction and information reconciliation, which you take the imperfect bit string that Eve has some knowledge about and make it into a perfect bit string. So error correction ensures that the bit string that Alice and Bob have, that after the error correction step, they both hold the same bit string. Still, Eve might have some knowledge about it, but at least the bit string they have, those are equal bit strings. And then the information reconciliation process minimizes the knowledge that Eve has about this bit string, so that in the end, Alice and Bob share the same random bit string that Eve has no knowledge about, so they can safely use it in the one-time paired encryption scheme, for example. And indeed, for this protocol, for this BB84 protocol, there exists a security proof. So this is a protocol that provably gives secure keys. So this was the first video of the series of videos about the security of quantum key distribution. I hope you have enjoyed it. I hope you have learned something. And next time we will talk about some mathematical concepts that we need to describe quantum key distribution protocols. We will talk about quantum channels and measurements. And we will also talk about some theorems that appear in the analysis of the security of those protocols. So I hope you've liked it. Thanks for watching and maybe see you next time.